Hey guys, welcome back. This is Jonathan Gardner lecturing on Sergey Lang's Basic Mathematics. In this section, we're going to cover inequalities. So I'm just going to give you the summary here of what the rules for inequalities are. Basically, inequalities work like equations. If you have a less than b and you multiply both sides by negative, then that's the same. When you multiply both sides by negative, you have to flip the signs. So you basically have to flip it when you multiply by negative. That's the entire shtick with inequalities. But we're going to go through and we're going to have some fun with math talking about how this works and why it works. So if we write a is greater than 0, that means a is positive. Those two things are the same thing. So positive means it's not 0 and it's not negative. If a and b are two real numbers, we're going to write a is greater than b. What that means is if you start with a and subtract b, then you get something greater than 0, which means that this difference is positive. Okay, and if we write a is less than b, then that means that b minus a is positive, or you can say negative a minus b is positive, or any number of things like that. Or and also we can say that minus a is less than 0 means that a is greater than 0, right? If the negative is negative, then the positive, if the minus is negative, then the not minus is positive. Phew. Okay, so that's in a nutshell what these different things mean. If you're thinking about how to build this from first principles, it's a very interesting topic, but most people that are approaching algebra don't really care about first principles. As a logician and doing mathematics, this becomes really fun stuff. Okay, so let's do a quick example. Let's use this purple color because it happens to be first in my bucket. So the quick example is this. We have 3 is greater than 2, right? And that makes a lot of sense, right? You learned that in elementary school, hopefully, and that's not news to you. Okay, other ways we can write that is we could say 3 minus 2 is greater than 0. These two things mean the same thing, right? What we're doing is, I guess you can think of it as subtracting 2 from both sides, but really this is saying that 3 being greater than 2 means that when you subtract 2 from 3, you're going to get a number greater than 0. Okay, and we also have minus 1 is greater than minus 2. And why do we know that? Because if you start with minus 1 and you subtract minus 2, that's greater than 0, because this is minus 1 plus 2, which is the same as 2 minus 1, which is 1. Okay, and of course 1 is greater than 0. Geometrically, if we have a number line, so let's draw a number line. Let's kind of look at what inequalities do. So we have our 0 here. Okay, if a is positive, that means a is over here on this side of the line. Okay, and if a is greater than b, that means b is somewhere in this region. So b could be here, or it could be down there, could be anywhere. That's when a is greater than b. That's what that means. Okay, now so for instance, in this case, 3 is positive. So a is, if 3 is over here, let's say 3 is here, and 2 is right there. So 3 is positive, and 2 is positive, and 3 is greater than 2. That's what that means. Okay. Now negative 1 is over here, and negative 2 is over there. Let's say negative 1, negative 2. This is not to scale, obviously. Negative 1 is not positive, but it is greater than negative 2. Okay. That's what that means there. So that's kind of the way to look at this. All right, and there's another symbol we have. We say A is greater than, he has a double bar underneath. I'm just going to put a single bar. A is greater than or equal to B. That means A is greater than B, or A is equal to B. A and B are the same. Those are the two possibilities there. So A is greater than or equal to. And so we can write, both of these statements are true. We can write 3 is greater than or equal to 2, but 3 is also greater than or equal to 3. So both of those are correct. Right. All right, now we are going to take advantage of that last section where we had the two properties for pos 1 and pos 2. Okay, let's go back and review that really quick. More because it was 3 sections ago. No, 2 sections ago, section 3.2. But also because we're going to be using that. So in these, pos 1 was, let's write this down. I could have used note cards, but I didn't know I'd actually need them. Pos 1, if A and B are positive, then A plus B is positive and A times B are positive. So pos 1 says that if you can add or multiply positive numbers, you'll get another positive number back. And then pos 2 said that if a is a real number, then if a is real, then a is greater than 0, a is equal to 0, or a is less than 0. One of those three. One of those has to be true. Not more than one. Only one. Only one of those is true. Okay, so going on to inequalities, we're going to have some new rules. We'll write down N1. This says if A is greater than B and B is greater than C, then A is greater than C. So we just write down A is greater than C, B is greater than C. Okay, we can call this the transitive rule. Okay, N2 says that if A is greater than B and C is positive, let's write C is greater than 0 with a terrible greater than sign in parentheses, then we have AC is greater than BC. Okay, this isn't true if it's negative, but it is true if it's positive. Okay, and N3 is the one for negative. So N3 says if A is greater than B and C is negative, then AC is less than BC. So we have to flip the direction of the sign there. All right. So inequalities behave just like equals, like equations that you've seen before and you've played with, except the difference is when you're multiplying by a negative, you have to flip the direction of the inequality, which is normally not a big issue. The problem is sometimes when you multiply by a number that may or may not be negative, you don't know because it has a variable in there that could be any number of values, then you have to take both cases and evaluate them separately. One where it is negative, one where it isn't. And so you have to basically take your inequality and break it down into two different inequalities. Okay, so let's look at a practical example of why this is. So let's start with 1. 1 is less than 3. Okay, now if we're going to multiply both sides by -2, so we're going to multiply by -2 and we'll multiply by -2, then what we get, if we didn't know this N3 rule, we might be tempted to write -2 is less than -6. But -6 is all the way over here. It's obviously smaller than -2. So this is incorrect. That's wrong. We should have written 2 is greater than -6. -2 is greater than -6. So when we multiply by these negative numbers, we have to flip that sign. All right? But of course, if we multiply by just regular integers, like if I just multiply by 2, not regular integers, positive integers, then we have 2 is less than 6. And that works out fine because 2 is over here and 6 is over here, right? And 2 is definitely to the left of 6. Okay. Now we're going to prove these rules, but if you're just interested in the rules and you're not interested in how things are proved, that's fine. You can just skip the rest of the video and go on with your life and get a good grade on your test. But we're going to prove these rules because we want to learn how math works and we want to become familiar with the process of proving things. Okay, so to prove N1. So to prove N1, if you recall, is if A is greater than B and B is greater than C, then A is greater than C. So suppose, we have assume, he says suppose, I say assume, I like assume better. A is greater than B and B is greater than C. Okay? So this means A minus B is positive and B minus C is positive. And this is a really good thing to remember, that when something is greater than something, the difference is positive. And when something is less than something, the difference is negative. Okay? All right, we're almost there. So what if we added these things to each other? We take a positive number and we add a positive number. What should we get? Well, according to the positive rule number 1, if we take a positive number and we add another positive number, it should be positive, right? So let's go ahead and work this out. So we have A here, we have a minus B, and we have a B. Those two cancel. And then we have a C. And what does this mean? Why, this means A is greater than C. QED. Cool. We just proved something using very simple algebra. Okay. So this transitive rule is, if we assume other rules, then we don't have to assume that this rule is true. Okay. To prove N2, I'm sorry my handwriting is so bad today, guys. It's summer. I've been exercising, and you got to exercise to keep your mind fit. To prove N2, suppose that A is greater than B. So we're going to start with A is greater than B. And C is greater than 0. Okay, so this A is greater than B means that A minus B is positive. Okay, and we know that when we multiply two positive numbers, which C also is positive, it's also positive, right? So therefore we have AC minus BC is greater than 0, or written another way, AC is greater than BC. QED. Yay, I think it's quod erat demonstrat. It's shown here, basically, in Latin. Makes you feel smart when you can say things like that. Okay, let's prove N3. Or rather, let's not. That's an exercise left for the reader. I don't want to deprive you of the reader/viewer. The reason why they do this, there's two reasons. One is either it's not very important and they don't want to spend the ink and the time to put together a solid proof of it. The other is that it's pretty simple for you to prove it if you've seen the other proofs, and this one should not be hard at all. It's going to follow the formula for N2 very closely. All right, now let's do some practical examples. Okay, so we have 2x minus 4 is greater than 5. Oh my gosh, I'm going to fail this test. What does this mean? Right? So we could remember that this is the same as 2x minus 4 minus 5 is greater than 0. We say that's the same as 2x minus 9 is greater than 0, which 2x is greater than 9. And oh, I think I know what I'm doing now. This seems to be a little easier, which is one way to do it. But the other way is just to remember that when you're using inequalities, it's okay to add stuff to both sides. So we're going to add 4 to both sides. So we get 2x is greater than 9. So we add 4 and that cancels that. We get that and we get that 9. Okay. Now the second question is, can we divide by 2? Can we move this 2 to the bottom? And the answer is, if it's positive, then you can. If it's negative, you can't. So since 2 is definitely positive, we can definitively say that x is greater than 9/2. Okay? All right, let me just kind of demonstrate what this means. So we have 2x minus 4 is greater than 5. So here's 5. And this is saying over here is 2x minus 4, and over here is not 2x minus 4. 2x minus 4 will never give you a number smaller than 5, but 2x minus 4 will give you a number bigger than 5. Equal to 5? No, but bigger than 5, yes. Okay, well, let's plug in this number we found. So we have 2 times 9/2 minus 4. That's the same. 2 cancels, you get 9 minus 4, which is 5. So definitely, anything over here is bigger than 5. Okay, so if we picked, let's say this is the result of 2x minus 4. Another way to look at it is if we had x. Let's put x here. This is 0, and this is 9/2. Okay, so x has to be greater than 9/2. Anything for x bigger than 9/2 will give you something bigger than 5. So let's pick something bigger than 9/2. Let's pick 10. 10 is definitely bigger than 9/2, right? So 10 times 2 is 20 minus 4. So we have 20 minus 4 is 16. So we plug in 10 times 2 minus 4 is 16. 16 is definitely bigger than 5, right? Let's pick something slightly bigger than 9/2. So 9/2, that's a little bit more than 4. It's 4.5, right? So let's pick 5. So we have 2 times 5 minus 4. Well, that's just 10 minus 4. That's equals 6. That is definitely bigger than 5 as well. So all these numbers work over there, right? And you can play that game for a long time if you want to. Let's do another example. This one's quite a bit more complex. It looks complex. It's really not that complex, but it looks complex. 3x plus 5, all divided by x minus 4 must be less than 2, less than 2, less than 2. Okay? Don't make the same mistakes I do. Do better than me. Okay. First of all, we note that x minus 4 cannot equal 0, right? That would just mean that you can't divide by 0, right? Well, what does x minus 4 can't be 0? That means x cannot be equal to 4. So whatever we get, x equals 4 is not a solution. Okay? Now, we're tempted to write it out like this. 3x plus 5 is less than 2 times x minus 4. But this is only true if x minus 4 is greater than 0 or x is greater than 4. If x minus 4 is less than 0, then we have to write 3x plus 5 is greater than 2 times x minus 4. If x minus 4 is less than 0 or x is less than 4. So you see this x equals 4 position, kind of, it's the dividing point between these two equations because we're multiplying by that. Okay, and again, the reason why we're doing this is because if x minus 4 is negative, then we have to flip the direction of that sign. Okay, so I'm going to draw a line down here. We're going to solve this side. So we have 3x plus 5 is less than 2x minus 8. Remember the distribution rule. You got to multiply this 2 by both terms, okay? So let's move the 2x this way. Let's move the 5 that way. So we have 3x minus 2x because it's crossing the side. We have x is less than, and we have minus 8 minus 5, so that's minus 13. Okay? Same thing happens over here. So we have 3x plus 5 is greater than 2x minus 8. Exact same thing is going to happen. So we get x is greater than minus 13. Okay? Okay? So we know that x cannot equal 13. But x can be greater than negative 13, or x can be less than negative 13. Okay? But wait a minute, hold on. This is only true when x minus 4 is greater than 0. Okay? Well, if x is smaller than negative 13, is it ever the case that this is going to be true? So no. This is never true. This is an important subtle win. This is an important thing here to remember. If x is smaller than negative 13, you're going to start at negative 17 and go down from there. You're never going to have a number that's positive. So this is never true. On the other hand, this is true when x minus 4 is less than 0. And if you plug in x equals negative 13 and bigger numbers, you note that at some point, okay, when x minus 4 is equal to 0, then this x no longer works as a value. So we get this for the possibilities, or x is less than positive 4. Okay, so x is less than 4, and x is larger than negative 13. So we can rewrite it this way. It starts at negative 13, is less than x, is less than 4. So x is any number in between negative 13 and 4. And that'll satisfy this inequality. And to check that, let's plug in some numbers. So let's plug in negative 13. So we have 3 times negative 13 plus 5 all over negative 13 minus 4. We're going to see if that's less than 2. Now it says that this is not a solution, but this is the beginning of the solution. Okay, so we have negative 39 plus 5 all over negative 17. It's supposed to be less than 2. Negative 39 plus 5 is negative 34 over negative 17, which is equal to positive 2. Okay, so this is one of the edges. This is when both sides are equal. But this is not a solution. Negative 13 is not a solution because x can't be 13. So this is at the edge. On the other end of the edge, we have x equals 4. So we have 3 times 4 plus 5 is all over to 4 minus 4, and that's supposed to be less than 2. And here we have a problem because that's 0. So we basically have, what is this, 12 plus 5, doesn't matter, 17 over 0. So it doesn't make any sense. Blah, you can't do that. Let's try something smaller than 4. Let's try, I don't know, let's try 3. So 3 times 3 plus 5 all over 3 minus 4 is supposed to be less than 2. So 9 plus 5 is 14 divided by negative 1. So we get negative 14 is less than 2. And indeed, that's true. Negative 14 is less than 2. Let's try something slightly larger than negative 13. Let's try negative, I'm running out of room here. Let's try negative 10. So 3 times negative 10 plus 5 all over negative 10 minus 4. It's supposed to be less than 2. So we have negative 30 plus 5 all over negative 14. So this is going to be negative 25 over negative 14. Is that supposed to be less than 2? So that's 25 fourteenths. Is that less than 2? Well, 28 fourteenths would be 2. So 25 fourteenths is less than 2. Okay, so hopefully I've satisfied your curiosity with this problem. It seems a lot more complex than it is. The critical thing is when you're multiplying both sides by x minus 4, you have to take into account that x minus 4 could be positive, it could be negative. The other key here is you have to pull out, put your math hat on for a second and look at the answer and see if that makes any sense. Okay, try to reconcile it with the assumption for this half of the equation. In this case, this doesn't reconcile at all. But this doesn't reconcile at all. This side does, however, and gives us this nice range, which is the solution. Okay, sometimes you'll get some from one side and some from the other side. Sometimes you'll get nothing from either side. It's just nonsense. Okay, we'll find out what happens next. Okay, so moving right along, the set of numbers x such that 3 is less than x is less than 7 is an interval shown in the next figure. So 3 is less than x is less than 7. We're going to draw this. So here's 0, 1, 2, 3, 4, 5, 6, 7. Completely evenly spaced. As you can see, I'm magnificent at spacing my number line. And that's sarcasm for you guys. So we can start at 3 and go up to 7, but we can't include 3 or 7. That's the range of possible values of x. Okay. We could also have 3 is less than or equal to x is less than or equal to 7, in which case we'd have the same range. 1, 2, 3, 4, 5, 6, 7. So here's 3, here's 7, except we can include 3 and 7 in the solution, right? All right, and this is the part where we lecture you on intervals, which is actually part of the first part of Selesnik's chapter on calculus. And he talks about open intervals, closed intervals, half open, half closed. You can read the definitions in the textbook. To be honest, we don't really do, we know that they exist and they're interesting, but I actually don't use them that often. So there's infinite intervals as well. I could run through them right here, but I think that this topic has been hashed to death and we should talk about the exercises now. Okay, so the first exercise, prove n3. That shouldn't be too hard. Look at the proof for n2. Okay, the second half, prove that if 0 is less than a is less than b, and if c is less than d, and c is greater than 0, then ac is less than bd. So this is just using, I think, n1. Yeah, n1. And the next one, similar things, except c and d are not negative. Okay, so you just have to remember which one's positive, which one's negative. 4, if x is less than y and x is greater than, prove that 1 over y is less than 1 over x. This one you can do a number of ways. One way that I want to show you, you can just multiply both sides or divide both sides if you wanted to, making sure that they're not equal to 0. Okay, and remembering that when you multiply both sides, if it's positive or negative, it changes the result. So the question is, if x is greater than 0, is 1 over x greater than 0? Right? If you know the answer to this, then problem 4 becomes rather easy. Okay, and problem 4b has the cross multiplication of inequalities, which says that if the denominators are both positive, then you don't have to flip the signs. But if they're both negative, you don't have to flip the signs either because you flip them twice, basically. Okay, problem 5. Prove if a is less than b and c is any real number, then a plus c is less than b plus c. Also, a minus c is less than b minus c. That's pretty easy to do. Just remember that if you have x is less than y, that's the same as saying x minus y is less than 0. So you can move this guy to the other side. Pretty easy stuff. 6, another proof. This is using squares. Okay. The caution that I have about squares, so we know that a squared is always greater than 0 because we haven't learned about complex numbers yet. But a cubed, if a is greater than 0, if a is positive, then a cubed is positive. But if a is negative, then a cubed is also negative. Okay, and that's the same for all the odd powers. So think about why that is. So this number 6 is for positives. Number 7, we use number 6 to do fractional powers, roots, right? So the question is, what's the square root of a? What's the nth root of a, right? If a is positive, is that positive? What about when n is odd? What if a was negative and n is odd? What's the cubed root of a? Is that greater than 0 if a is less than 0? Or is it less than 0? Which is it? What number times itself 3 times would get you a negative? Okay. A, B, and C, D are numbers. Number 8, and assume B is greater than 0 and D is greater than 0. Assume that AB is less than CD, which I think comes from the cross multiplication in 4b. Assume that is true. Prove this complicated thing, this mess. I encourage you to tackle 8. I remember doing 8 with my kids. It was a lot of fun. And using the cross multiplication rule. So you have let's just write this out. A over B is less than A plus C all over B plus D is less than C over D. This is really two statements. One says that A over B is less than A plus C over B plus D. And the other says that A plus C over B plus D is less than C over D. Okay, and then you can look at these and do the cross multiplication rule if you really wanted to. All right. B, R is a number greater than 0, prove blah. That should be pretty easy. If 0 is less than R is less than S, so the R and S are positive, prove that the following equation also holds. Okay. I think, if I remember correctly, and I haven't done 8 in a while, it leads to a glorious mess with fantastic simplifications. So if you have problems on 8, I highly encourage you to reach out. Let's go over it together again. I had a lot of fun doing 8. 9, if 3x minus 1 is greater than 0, prove that x is greater than 1/3. That should be pretty straightforward. 4x plus 5, number 10, same thing. And numbers 11 through 32 are all inequality equations you can do to practice what you learned. So hopefully it should be fairly straightforward. I hope you guys enjoyed this section. Catch me next time. We're going to cover the final section of we're done with chapter 4. Chapter 3. We're in chapter 4 next. Quadratic equations, which if you have any experience in algebra, you probably remember this as being one of the most boring and tedious and useless parts, but he is going to take less than 3 pages, cover the entire subject for you. So you'll see me next time. Take care and bye-bye. Hey guys, thanks for watching this video. This video is part of my series on Sergey Lang's Basic Mathematics. You can click here to watch the rest of the videos in the playlist. You can click here to learn more about me, and you can click here to support my channel. Thank you so much. Bye-bye.